Hello and you're very welcome to Adapt Radio. My name is Dr. Claire O'Connell and today we are talking about AI and marine awareness.
From the Adapt Centre at Trinity College, this is Adapt Radio, presenting groundbreaking innovations one conversation at a time.
Having this many sensors in an environment is a very exciting concept. The impact that those can have on the environment and also to help us monitor activity that's happening in our waters, in the Irish territorial waters, as you mentioned, are some of the largest territorial waters in Europe. To understand what's happening in our waters is a big challenge.
Now, as an island in Ireland, we are well aware of the oceans and seas all around us. But how do we monitor them effectively? Well, today's guests are exploring how undersea cables can help to spot things in the ocean. Professor Marco Ruffini is Professor in Computer Science at Trinity College Dublin, and Dr. John Kennedy is Associate Professor in Vibrations, Acoustics and Dynamics, again at Trinity. They are co-leads of the Seascan project, which is using existing fibre optic cables in the seabed to create a network of underwater sensors that can detect what is in or on the water. Marco and John, you're both very welcome to the programme.
Good morning.
Thank you, Claire.
Seascan sounds like a really ambitious project. What do you aim to do with the fibre optic cables? How does it all work?
So it works by sending optical signal down a fiber. So there are different technologies that can be used for sensing. In this case, we are concentrating on one which is called distributed acoustic sensing. There is a machine that basically sends a laser pulse down a fiber, and it detects the backscatter, which means the little bit of signal that sends back to the source from the fiber. And then by checking how the phase, because light is a wave, so it has a phase, so how the phase changes across the fiber, it can detect any kind of strain or vibration in that. So basically, the fiber is so sensitive that any even small vibration can be picked up by this. And because sound waves are basically nothing else than vibrations, it can basically detect the sound waves just as if it was a microphone or an hydrophone in case of the sea.
Wow, it sounds incredible. I mean, you think about these networks of fibre optic cables are already in the seabed, because these are the cables that we rely on for telecommunications, isn't that right? So they are already carrying information around the place. So you are basically using them as acoustic sensors in the water to detect the kind of the vibrations that are happening from whatever is going on above them in the water. Is that right?
Yes, exactly. And I mean, the key is exactly what you said, that this network and those fibers, cables are already in the water. In fact, I mean, there are other technologies which are even more sensitive, based on hydrophones, for example, which can pick up signals with higher sensitivity, higher resolution. But the problem is that these are very expensive and, they have to be laid down in certain conditions and so on. While the key of this project is that, we just use fibers that's already there, has been there for 5, 10, 20 years for other uses like telecommunications, but we just use part of the fiber, to send out this probing signal and receive any signal, detect anything that happens. And the interesting thing is that, if a fiber is 100 kilometers long, just by placing one device at one end of the fiber, I can replicate the case if I had a microphone every meter. So I can get a different sound every meter for all the 100 kilometers just with one device at one end.
Wow.
So you can see that, this is a lot easier to use. And the key is to use existing technology. So the only cost is really the cost of the additional device. You don't have to lay out anything else. There's no maintenance cost or anything.
Okay, brilliant. And what kind of things might you be wanting to monitor in the water? John?
Yeah, so this is very interesting. So from my point of view, in the world of acoustics, having this many sensors in an environment is a very exciting concept. And really, there's going to be a lot of different noise sources, both natural and sort of from human activities underwater, and the impact that those can have on the environment, and also to help us monitor activity that's happening in our waters, in the Irish territorial waters, as you mentioned, are some of the largest territorial waters in Europe. And to understand what's happening in our waters is a big challenge. So the power of the sensing technology, as Marco says, is to give a very high resolution, spatial resolution, a sensor every meter, over hundreds of kilometers. And to do this from a land-based piece of infrastructure, very exciting. So from my side, I see a signal coming in and I look at that from an acoustics perspective. It'll have different frequency contents and that will help me understand what I'm seeing in the signal. And from the point of view of vessels going by, each different category of vessel will, whether it's a ferry or a small fishing vessel or whatever it might be, will have different propulsion, different hull. It'll have different sources of noise in the vehicle. And there's a sort of a unique acoustic footprint for each one of those different types of vehicles. And why we might be interested in that, is that the sound that these vessels produce has an impact on the sort of the marine ecosystem, as well as trying to understand where the vessels might be from our perspective.
So you can pick up all these signals just sitting in your office on land in Ireland. And as you say, the marine territory of Ireland is, I think, 10 times the landmass. So it's a massive, massive area. How much of it would you anticipate covering with this network of sensors?
So the idea is that, they're fibered because Ireland is an island, of course, and it's on the west coast. So it's the first point of access, let's say, from all the fibers coming from the Atlantic. So there's a lot of fibers that actually land here in Ireland, going from the Atlantic, and maybe then hop again towards the rest of Europe. So, we counted at least there probably are around 20 fibers as of today that could be used for this sensing. And the idea is that this is at the beginning, Syscan is an exploratory project. We know that we can sense things, detect vessels. The scope of Syscan is to detect what's called dark vessels. So vessels that are supposed to send a beacon to tell everyone, I'm here, this is me, this is my speed, that's where I'm going. But instead, for some reason, they turn it off. So that's the concept of the dark vessel. And the idea is that, you need to have another source, which is not what's called this AIS, which is this beacon. So you need a different source to really check if a vessel is there or not. So this is exploratory, but we're already seeing that it's very easy to detect the presence of a vessel. We can see that it's very likely that's possible also to identify the vessel that it is. And so, one option is that to start laying some more of this fiber just for sensing purposes.
Okay.
So, there is going to be an additional cost, but it's still much less than any other technologies, that could be used, like hydrophones.
Okay.
So, and if you start doing that, of course, then you're going to have a much wider coverage. And the important thing, because, we've been talking to the defense forces and so on. What they want is not that they want a system that's absolutely correct. They want just another layer of information, really. They will have their sonar, they will have some radar. But the more independent information that you can mix together, the more reliable thing is. And that's key. Also because if one goes offline for some reason, you have a completely independent system that's still functioning. It works as a backup or as an additional information.
Okay, so you can get that bigger picture, or you have kind of a remaining line of inquiry if others go down. John, you mentioned there sort of sensing things in the water and how you would be able to sense the signatures of various types of man-made craft. What about sort of animals or plants or things like that you might want to pick up in the ocean? How sensitive would it be for tracking things like types of fish, migration patterns, things like that?
So that's a very interesting question. And I suppose we'll see a lot of different signatures. As Marco's highlighting, we might be primarily interested in the vessels going past, but there will also be, distributed acoustic sensing is used for seismic monitoring, so you'll see any activity like that. You will also pick up certain marine species that, depending upon the frequency range you're looking at, you'll see calls and signals from different species. And this is where perhaps, my background as an acoustician is really in understanding how the sound's propagating through the water and what generated that sound in the first place. But there would be potential for this project to have a broader scope and interact with marine biologists who might understand the different species that they might be interested in monitoring in Irish waters, and that might be interesting as well. But to bring it back to the vessels, one of the things that you might be interested in monitoring is how the noise produced by vessels could impact breeding behavior for different fish species and other sort of economically important activities that are in the water. And as we're interested in doing stuff like building, significant amounts of offshore wind in Ireland. And if you look at other countries who are doing this, in particular, maybe Japan has looked at some strong studies about how the installation of an offshore wind farm produces some underwater noise, impacts the breeding grounds for different species, species and then has an effect on, fishing in that area. I suppose as long as you know what's happening and what's going to happen, you can plan accordingly and you can make decisions which have the best environmental outcomes. So shipping noise has a sort of a much broader impact than you might initially think.
For sure.
But the first thing that we're trying to do here, as Marco says, is identify what vessels are passing by these cables and in particular looking for any unusual activity that may be happening in the area.
And where does AI come into this? I assume you get an enormous amount of information back from the sensor network. Is that where you apply AI to make sense of it?
Yes. So, and the key, in fact, to be honest, the devices we are talking about, they're called interrogators. These are commercial devices. In fact, these devices have been around for 20 years. Okay, so fiber sensing is not a new thing. The new thing is using existing fiber for fiber sensing, because fiber sensing has been used like in oil wells. It's a very good sensor. It's not electrical. It doesn't have sparks. It doesn't make things go on fire. Mm-hmm. So fiber sensing is using bridges to monitor the state of the bridge. A lot of application. But recently, it came up the idea that because we have like billions of kilometers of fiber around the world, if we just could reuse this fiber for sensing, then of course, this is going to be a big advantage for some number of applications. Collecting the data, though, is something that's commercially available, but it's really what you do with the data afterwards. And as AI and machine learning have come up, both in terms of algorithms, both in terms of the hardware for faster processing, have come up recently. So we use basically machine learning to identify these patterns. And the concept is quite simple, okay? So with this DAS device, you pick up a signal, okay? And it's a signal, it's an acoustic wave, composed of different frequencies that comes from the vessel. Now, by itself, the signal, might tell you that there is something, but you really don't know what it is. The important is to correlate the signal with another source of information. So in this case, for example, there is this famous messaging layer. It's called AIS, and it's used by many marine vessels. It's used all over the world. It's been there for many years. So this beacon tells you in parallel, because this is transmitted by the vessel itself, tells you the parallel, what vessel it is. And then you can go into a database with the vessel ID and check the size of the vessel, the tonnage, the type of vessel and so on. But then it also gives light data like speed, direction, where it left, and so on. So the idea is that now you correlate this signal that you get from the DAS with this additional metadata or information that you get from the AIS. So the machine learning algorithm learns that a certain type of signal is always produced by this same type of vessel. Okay, that's it. It's very easy. And that's what all supervised machine learning is. It might look like fancy AI, but a lot of it is about here's a signal, and that's what should be. And then you put it together. Now, of course, there's a process called training, and you cannot do this just once. So you need quite a lot of data to do it. But after you do it, then there is the complexity of the algorithm. Depends on the complexity of the data, how many data you have. There's a lot of theory behind this, how do you optimize correctly. But if you do your work correctly, then with a quite high percentage, you can be able to identify that when you see a signal, even without the AIS, so take away the AIS information now, once you train your signal, the next time you get another signal, you look at this and the system is going to tell you, I've seen this before, it looks like a stena line. Mm-hmm. Or else, if it doesn't look like anything, it's something new, it's probably going to tell you, I haven't seen this, but this looks in between a stena line and a cargo ship. Right? So it tells you also that. And then there is a lot more that, we're going to be investigating over the next few years, something a lot more specific than this. But this is like the very high level description. But I think it's very intuitive. Like if you let it say something and you tell what it is, then it learns how to associate them. And then even when it doesn't say the additional information anymore, it's able to say, I recognize this.
It recognizes that acoustic signature by itself.
Yes.
Yeah, very good, very good. Tell me how the project came about.
Yeah, so it came about because we seen there was an open call from Research Ireland. It's one of these challenges. And in this case, it's challenges with the defense forces, where they have 4 different type of challenges, and they were looking for applications. So we applied for the marine challenge of identifying dark vessels. The idea is that I work in optical communication. I've been doing that for the last 20 years. Fiber sensing is growing exponentially. The interest around fiber sensing. So we started doing some work on fiber sensing. So when I saw this call, I thought, this sounds like something like fiber sensing would be very good at. And I know that in the past, people have done a little bit of this work. Other researchers, like following whales migration, as you mentioned before, that has been done that. I know that some people have published some early papers saying, if there is a vessel, it's likely that you can see it. Although it wasn't systematic as we're doing now on having multiple vessels and so on. So that's the way. So I applied, I was looking for support, as in, I was thinking what's really needed to do this project. And then, what other skill set are there here in college? And then through some colleagues in engineering, I happen to know that John Kennedy is working on acoustics and, over the air, but also the kind of similar when you go underwater. And so I asked John if he was interested in joining this, and John, yes, was very interested. That's how it was formed. And then, you write an application like any competitive funding. And then I think they selected 10 out of, I don't know how many applications were in there. Now, this is a kind of unusual funding for us because it goes into very short timescales. So basically you get funds for the first 3 months. And then the first 3 months, you have to build a case that your project is worth pursuing into a first prototype. So 10 projects went into that phase and only 5 were supposed to be selected for the second phase. So we got selected for the second phase. This goes until December. And now we're basically running for the final phase where they will pick one across the 5 projects to decide, to continue this further.
Brilliant. And John, what made you so keen to join Marco in this project, Seascan?
One of the exciting things about working in acoustics is that it sort of touches all aspects of human activity and also our daily lives. So over the years, working in acoustics has been very exciting because, you get all sorts of different people knocking on your door saying some aspect of my project or my problem involves something to do with noise or vibration or something like this. And as an academic working in this area, my expertise is in the physics of what's happening. So I can apply that expertise to any different application that might come up. And I had been aware over the last few years of a growing concern and interest in underwater noise exposure and the underwater environment. And as somebody who's worked a lot in, air and what happens to human activities on land, I've been very interested over the last few years in trying to transfer some of the knowledge and the expertise and the background that we have in Trinity to this emerging awareness of the underwater noise problem. So I was very excited to see this because this technology gives you a kind of unparalleled resolution of sensors underwater. It allows you to investigate questions that, are very important for various different reasons. But there's also a challenge there. It's like, how do we interpret and understand the signals that we're seeing? So Marco mentioned that we need a large database to train the model. But when you're training the model, the better the data that you can give the model, the more successful its training phase will be and the more accurate and precise its predictions will be after that. So when you get a raw signal coming off the sensor, that's a very basic level of information for the machine learning or the AI to work with. And my background in signal processing, there's a lot of different ways we can look at acoustic signals, breaking them down by frequency content, looking at, the time history of the signal. And essentially, my thought here was this is a very exciting project, and I could immediately see how some of the expertise and background in my research group could aid the project. So it's the perfect mix of seeing something new, seeing something exciting, and then seeing that we have valuable skills and expertise in the group that could make a real contribution there. So it was a nice alignment of several different things.
Great. I mean, you mentioned there that a lot of your previous work has been in air. Water is a very different medium. Is it an easy enough transfer? What kind of correction factors do you have to incorporate into the work when you're moving from land to ocean?
So I suppose there's a lot of similarities, but as you say, there are physics that happen underwater that you don't have to consider as much in air. So when we're talking about, how sound propagates in the environment around us, it's going up into the atmosphere and there's different layers of the atmosphere at different temperatures. As the sound moves through those different layers, the path of that sound is bent in different ways as it moves from layer to layer. This is why if you're listening to, there's a concert in the Aviva Stadium or something like this, you might hear that sound several kilometers away, whereas a house closer to the stadium may not actually hear it. And this is because the sound is being bent and changed its path through the atmosphere due to the different temperatures in the atmosphere. Underwater, that's much more significant. I mean, we have different layers of, different temperatures, different salinities, all these different things underwater influence how sound is propagating in that medium. So whereas in air, we might often be able to take some simplifying assumptions and ignore these things. Underwater, if you want to identify the location of a sound and how that sound has propagated from the source to where you're measuring it, you have to be much more careful and be much more aware of the medium that the sound is propagating in.
So I suppose moving back out of the sea, what other kinds of applications could this technology be used for, maybe on dry land?
In fact, the potential of this technology in dry land is even higher than on the sea because of that, as I say, I think 5 to 8 billion kilometers of fiber that are around. Only maybe a few millions or a few tens of millions are on the sea, but all the others are on land. So there's a huge amount of fiber on land, both buried fiber, so under the surface of the roads, but also what's called aerial fiber. So, it goes on poles like the electricity, for example. And of course, that fiber is also sensitive to different type of vibration. For example, I've seen work at conferences of people able to count the number of vehicles going across the road, able to see if there was a car or it was a truck by counting the number of axles in the car, for example. I know, it can be used for earthquake detection or any land motion. I've seen people naming loads of other applications. For example, for aerial fiber, you could sense the presence of drones. Okay, for example, you could put a perimeter around an airport, for example, and because it senses noises, you can sense the noise created by a drone and see, if how far or how close a drone may come to the airport. And because, it's an issue, drones, even recreational drones are not allowed to fly near the airports because of the dangers that could interfere or hit an airplane. That's another example of an application. And then, even for monitoring itself, we're talking about here a lot of use for third-party application, but another key use of the fiber is to protect the fiber itself. Because you can monitor vibration in the fiber, of course, you can monitor things that are approaching the fiber. Of course, we have heard, it becomes quite popular now to hear that undersea cables, have been cut. But the idea is that, anything that approaches close to the cable, now you can actually hear it, especially if it's dragging on the ground or even touching the cable becomes very evident something happening. But this also can appear on land, right, for other reasons. For example, it's, you won't believe how often for a country, right, for a national operator, how often they get fiber cuts due to digging. Right? It doesn't seem there is digging so much, but if you take a nation, somewhere there's always some digging. There's probably 10 to 100 places where some digging is going up, either for repairs or for building, for constructions. If they pick up a fiber, they will just break it. However, you can detect the noise of the vehicle, that is trying to dig. And, that can come up and you can detect that maybe 10, 15 minutes in advance, actually reaching the fiber. And then you can just alert whoever is doing that because you also have the location where it's happening. So you can just alert saying, stop digging because you're going to hit the fiber. So there is, and then again, in Ireland, we know there's lots of storms, so when there are big storms, the electricity goes down because the poles go down. That's another thing that you can detect things happening in real time. So there's a lot of application, I think, even on the terrestrial side.
It sounds absolutely fascinating. What are the next steps for the Seascan project?
Okay, from my side, I look in more at the high-level machine learning and maybe the deployment issues. The other side is to improve the machine learning techniques. As I mentioned before, there's a lot of tweaking that you can do to machine learning in the way you produce the data to the algorithm, or the way you select an algorithm, the way you choose parameters for an algorithm. So the idea is to try and make this as sensitive as possible. Also to have, of course, strong interaction with the stakeholders because they might want specific application. And the idea is that you can train the algorithm to recognize these specific applications. And then it's all that they say, how do you make it practical? How do you deploy the system in a way that's cost effective? How do you send the data from the system back to the operation center in a way in live? Because at the moment, what often happens is that you bring a device where there's a fiber, you record it for a number of weeks, and then you bring it back into the lab and then you analyze. But of course, if you want this to be operational, you need real time. So how do you bring the data back into the system? And then obviously, how do you merge this information coming from this marine DAS system? How do you merge that with other sources of information that might be available from the stakeholders?
So from the acoustic side, I feel our role in the project is to increase the accuracy and the precision of the system once it's been deployed in practice, to move beyond an event detection and into a detailed classification of that in terms of what we're seeing, what speed the vessel's traveling at, what class of vessel it is. And these things can be seen in the acoustic signals that we get from the system. And from my side, it's very exciting to have this growing database of signals to work with and this more and more nuanced understanding of what we're seeing underwater around the Irish territorial waters.
Our thanks to Professor Marco Ruffini and Dr. John Kennedy for joining us today. And if you would like to find out more about Seascan and research more generally in this area, you can find lots of information in the show notes and at www.adaptcentre.ie. That's it for the podcast this time around. Until next time, from myself, Claire O'Connell, Slán, and thanks for listening.
The Adapt Radio podcast is brought to you by the Adapt Centre at Trinity College Dublin. Find out more about their extensive research work at adaptcentre.ie. Join us next time to hear about more groundbreaking innovations. To get new episodes automatically, just click the follow button on your player right now. The Adapt Radio podcast is produced by dustpod.io with episodes monthly on Apple, Spotify, and wherever you get your podcasts.